Relations and functions. A relation is simply a set of ordered pairs. And that's shown here. So we've got a set with the squiggly brackets. Inside it, we have a point and an ordered pair, and it's simply the connection shown between two variables, perhaps x and y. So as an example, when x equals -10, y equals 2. When x equals 7, y equals 3. The domain of the relation is simply the first number in each of the ordered pairs. So -10, 5, 7, 9, 9, 12. Please note, although we've got two 9s, we only list it in the set of domain as being once. We don't need to show it twice. The range is the second number in the ordered pairs. Again, we've got a repeated 3, but we only show it once in the range. Now the relation, the connection between these two variables can be shown in various ways. So as a set of ordered pairs, as a mapping diagram, so here we have our domain, there we have our range. Notice that the value 3 can be achieved by a 9, but also a 7 in this relation. The value 9 produces a 3 and also produces a 6. So there's our domain, there's our range. In some ways it's really good to think about the domain as being the input to a machine and the range as being the output of the machine. So you throw -10 into the machine and it produces a 2. We can show a relation as a table of values. And we can also plot it on a Cartesian plane. Again, you can see when x is 9, we have two y values for this relation. And we can also have an algebraic rule if we can see a clear rule that exists between the two variables. But in this case, it's all very random, and so I'm unable to produce a rule. The implied domain for a relation is just basically where the rule has meaning. So what values can we throw into the rule so that the rule has meaning? So as an example, here we've got y equals x cubed. So we can imagine the shape of that. We go up like so. So we can have any real value for x. So the implied domain is R, the set of all real numbers. However, if we look at the rule y equals the square root of x, we know that we cannot find the square root of a negative number. So if we substitute x equaling -4, we will not produce a y value. So -4 should not be included in the implied domain. So with the implied domain, for where does this rule have meaning, we're going to consider the x values which are greater than or equal to 0. We've dealt with interval notation before, but as an example, if we begin from A and include A and go and try to obtain positive infinity, then this here is our implied domain. The values of x which are greater than or equal to A. In this situation, we're starting at A, square bracket, and including it, and going up to B, but not including B because it's a circular bracket. So here we have our implied domain. X is greater than or equal to A, but less than B. If you like, that's a domain restriction that we have. Describe each of the following using interval notation. We've seen this before. Here's our number line, and we just need to put it in interval notation. So we're starting from -3, going up to 5, but not including the 5. -3 up to 5, circular bracket for the 5, square bracket here. Here we have two sections, so we're going from 1 to 3, not including the 3, so square bracket 1 to 3, circular bracket. The second part is we're starting at 5 and approaching positive infinity, so square bracket for 5, then infinity, circular bracket, and we're considering them both, so it's in union with, we've got them both. State the domain and range of each of the following. So here we have an ordered pair, and remember the domain is simply the first number of each of these, so 1, 2, 3, 4, and it's in order of lowest to highest that we listed, squiggly brackets. The range are the second numbers, so 2, 5, 8, 11, and there they are. B, we have a table of values. The domain 10, 15, 20, 25, 30. And the range, these are all our range numbers, but they're not in order from lowest to highest. So when we list our range, we just have to list it from lowest to highest. C, we have a parabola. So remember that extends on indefinitely in that direction. So approaching for x, negative infinity, and also over here, positive infinity for x. So we can have any real number for x. So the domain is R, a set of all real numbers. The values of y that we can have is anything above the x-axis, that is that y is greater than or equal to 0. That's my range. For the circle, my domain, I can go from -4 to +4, and the range also from -4 to +4, including those. So that's why it's square brackets. I will go over how you sketch these by hand in the next section, but for this part, you could either use your knowledge that you've had last year from year 10 maths, or also just simply sketch it on your CAS calculator. So if I've got a connection between x and y here, such that y is equal to the square root of x minus 1, then it will look like this shape here. So that point there is the end point, which is at 1, 0. And to look at our domain can be any value greater than or equal to 1. So x is greater than or equal to 1. And obviously, we can work towards positive infinity. If we do so, the values of y are going to get larger and larger. So our range for this is y is greater than or equal to 0. Part B here, we've got the rule y equals x squared minus 4. X is an element of the set 0 to 4, including the 0 and including the 4. So there's a domain restriction here for the x values that we can throw into this rule. Here's the graph of it. Turning point at 0, -4. And so that's the x value there of 0. If we substitute 4 into the rule, we'll get a 12. That's shown here. So there's the graph. The domain is from 0 to 4, including the 4. Our range is from -4 up to 12, including the -4 and including the 12. So that's why with the endpoints, I've shown those as solid dots. Functions, let's look at this definition here. A function is a special type of relation whereby each element of the domain, the x values or the input, has only one element associated with it in the range. So firstly there, a function is just a type of relation. So all functions by definition are in fact a relation as well. But when we consider relations, we can either say whether that relation is just a relation, or we can go further and say, yeah, it's a relation, but it's also a function. The key to this about deeming whether or not a relation is also a function is to look at this situation. If you throw something into the machine, it should only produce one output. If you throw something into the machine and there are two pieces of output, then we know that it is just a relation and not a function. Let's look at some examples here. We had this set of ordered pairs before. This is just a relation, and the reason for it is that with the domain, when the domain is 9, we have an output or a range of 3, but also at the same time a 6. So in other words, we throw 9 into the machine and we get a 3 and a 6. So therefore, it does not meet the definition of being a function. We can apply what we call the straight line test when we look at graphs. Whenever we place a straight line rather, on the graph, it should only cut the graph once. If it cuts it more than once, then we don't have a function. It's just a relation. So here for the parabola, you can see wherever I place a vertical line, it only cuts the graph once. Here we have a circle, and you can see where I place the vertical line, it will end up cutting the graph twice, so therefore we deem that not to be a function. Let's think about that. For this particular x value, we have 2 y values. So one element of the domain produces 2 elements in the range, therefore it is not a function. At first glance, this looks like a straight line, something in the form y equals mx plus c. But what we've got there is an entire region below that line, so we're considering this region. So with the straight line test here, you can see that this vertical line cuts the range, because the range is all this shaded stuff in blue, an infinite number of times. So therefore it's not a function. And we have various types of functions. A one-to-one function. For every x value, there is only one y value. So this function here is one-to-one. We have many-to-one. So the value 9 can be achieved by x equaling -3 or x equaling 3. So many x values produce the one y value. So that's seen as being a many-to-one function. This yellow box just tells us that what we're considering here is the number of x values to number of y values. That's why we have many x values produce the one y value. And back on this one x value produces one y value. All right, a problem. We're going back to relations here just to describe what type it is. So remember, it's x values to y values. Now, of course, this relation would not abide by the vertical line test, so it's clearly just a relation and not a function. And it's a one-to-many relation. So one x value produces many y values. For b, we've got a relation, and it's a one-to-one relation. It abides by the vertical line test, so we can say that it's a function. C is also a function, because it abides by the vertical line test. And here what we see is that many x values produce the one y value. So if we consider this value for y here, so there and there, it can be achieved by either x being that value, or if we went backwards, that value there. Now, of course, the circle does not abide by the vertical line test, so therefore it's deemed to be just a relation and not a function. And this is in fact a many-to-many relation. So this y value here and here can be achieved by many x values. So if we have x equaling that, it comes to here. And if x is over here, it also equals that same y value. So it's a many-to-many, as you can see. State whether the following are functions or relations, and we've just gone through the explanation of that, but again you can see I've applied the vertical line test and produced what I spoke about before for A, B, C and D. So looking at E here, we've got a set of ordered pairs. And what's interesting for us is that when x equals 9, y is 3 or 6. So therefore, it's not a relation. So we throw 9 into the machine and we get 2 pieces of output, so therefore not a relation. So you can see x equaling 9 produces a 3 and a 6. Relation only. For D, it's very different. For every x value, there's only ever one y value. So you can see here in the set of ordered pairs that there are no repeated x values with a different y value. All the domain elements are unique. Just to summarize for functions, remember that what we're looking at here is that for every x value, there should only ever be one y value. And we can always, looking at a graph, apply the vertical line test. Cuts the graph twice, so therefore not a function. There's nowhere I can place the vertical line, so it cuts the graph twice, therefore it's deemed to be a function. And don't forget that functions are a type of relation, a special type of relation.